Hello. It's October 13th for me in real time, but it you should be watching this video at the very least by October 16th. This video is intended to be a replacement for the class that we would have otherwise had in on October 16th had I not been compelled to be in Southern California for a conference. And so I'm going to be missing that Wednesday, the 16th, but also the following Friday on the 18th. I will also be absent. So I'll make probably two videos, is what I'm thinking. One, which is this one here, and then another one on Friday. And I hope that you watch these videos kind of in the same way that you um, uh, go to class. That is to say, like you are attentive, that you are not just passively consuming, but that you are actively interacting with the material in some way. Now, of course, that's going to be very difficult in terms of interacting with me and asking me questions or making comments toward me because we are, after all, separated in time and space from one another. And so it's very difficult for that to happen. It seems like a violation of the laws of physics. So fair point, but I think that there are things that you can do to sort of make it make a simulacrum of the classroom experience for yourself, which is what I would like you to be able to be what I would like you to be able to have the self motivation to do. So in particular, please have like a notebook out, please have a writing implement out, take notes, develop questions maybe and comments inside of your own head, and let's share those questions and comments maybe later, or maybe what I can do is open up some space. You can share it via email. Sorry, I could open up some space on the Canvas page or something like that, where we can interact about this stuff. But what I'm encouraging you to do is try to be active in how you are consuming these videos. I know all too well, as do I'm sure all of you, the what can happen when you are watching a, for example, YouTube video. Creators make it very easy for you to slip into a kind of passive mode of consumption, and I want to discourage that and encourage you to be more active. Uh, Simple encouragement. Can't tell you what to do, but I think that it would be to your benefit to do that. Okay. Oh, what are we going to talk about today? So I want to continue talking about that gadget that we talked about at the end of last class, which is representations of vectors with respect to a basis. So, well, maybe rather than me talking it all out, let's write stuff down and just reiterate that story. Okay. So, yeah, representations of vectors with respect to, oh, I'm doing it, with respect to a basis. And as we've said many times, mathematicians use this phrase with respect to a lot, and oftentimes will initialize it to WRT. And so I will be doing the same. All right, so here is the setting that we want to be working in today. Let's say that we have a vector space V, a vector space. And let's say we have a basis, capital B. And remember, a basis is an ordered set. And so we denote the fact that we have an ordering on it in the following way. We'll call the elements of the basis beta 1 through beta n. So, first point, I am going to make a finite list of vectors here for my basis because I want to work exclusively in the realm of what are called finite dimensional vector spaces. We should admit to ourselves that there are very important vector spaces which are infinite dimensional, but for much of the story that follows, bringing in particular, bringing in the machinery of matrices and things like that, things are simpler and easier to talk about when we limit our discussion to just finite dimensional vector spaces. There are aspects of infinite dimensional vector spaces which set them apart from the theory of finite dimensional vector spaces, which are very tight, very coherent, very well understood, and so we want to study that. And rest assured, you are missing out on stuff, but you're getting a tremendous amount of value out of just studying the finite dimensional situation. Okay, second point, we proved a theorem last time, which is that maybe I'll recall some of these theorems. So the theorem that we proved last time is that all bases of a vector space have the same number of elements. And we call this number of elements, we call that the dimension of M. The dimension of V. And maybe we denote it dim V. Okay. So the dimension of this vector space, evidently, is n, because I've written n vectors here in this basis. Okay. Another theorem that we proved, so that was great, and we know that, for example, Rn, the n tall column vectors, that's an n-dimensional vector space. The P sub n, which is the polynomials of degree less than or equal to n, has dimension n plus 1. And if we think about the vector space of m by n matrices, so m rows and n columns, that's an m times n dimensional vector space. Another theorem that we proved that we're going to be really writing hard today is that a basis, a collection of vectors B is a basis. So this is is a basis if and only if every vector V in big V can be uniquely expressed as a linear combination of elements in B. Yes, true. So part of this should not be surprising, right? We know that a basis B, by definition of the word basis, is any set that is spanning all of V and linearly independent, right? Those are the two conditions, spanning and linear independence. So the fact that it's spanning means that every vector V can be expressed as a linear combination of elements in B. But note that the real thrust of this statement is about this uniqueness. The fact that every vector can be written in exactly one way as a linear combination of elements in B. Well, that's the sort of conjunction of the two of linear independence together with the spanning condition. Those two things working in tandem is what gives rise to this unique expression as linear combination of the basis elements. Now, given that we have that kind of uniqueness, we can sort of then record the information of a vector using that linear combination. And if we have a fixed basis, what does it mean to specify a linear combination? Well, it means that you are specifying the coefficients that you used in the linear combination when you express that vector uniquely as a linear combination. Hopefully, okay. This is just the thing with linear algebra, right? And we're really getting into it, right? Where there's a lot of jargon, there's a lot of terminology, there's a lot of vocabulary. There is a almost a language that's around that gets developed within the space of linear algebra, okay? And what you are hearing with your ears is the kind of spew that can happen when you string enough of these words together. It can sound like just a gigantic jumbled mess of words that you might have some associations or feelings with, but I assure you, or how confident do I feel? I assure you that everything I just said is a sensible statement in linear algebra. And I think one of the things you want to be able to do for yourself is be able to speak that same language. Because and the problem is that very often students in linear algebra will string these concepts together in ways that just don't make sense. Like you say things like the basis of the vector, and nobody knows what you're talking about. And you say the basis of a vector. No, no, no. Bases are things that you apply to, or are things that are associated with vector spaces. Is that what you meant? And you're like, yeah. And then you say, okay, so then can you restate what you were saying? Yeah. So if you take the zero vector and you take its basis, and then the people who are fluent in linear algebra as a language, their heart sinks, their brain breaks, and they um, they have problems. Okay, they have serious problems. So this is every linear algebra student. Okay, so I'm not calling anybody out. Every linear algebra student goes through this phase where they spew out this nonsense, and it doesn't make any sense at all. We want to hone our language to get it to a state where we can speak fluently, or at least competently, in this language. So, just to restate what I said with all of that in mind, I'm trying to be extraordinarily precise in what I'm saying, okay? That's the sort of quality of mathematics that I particularly enjoy. But here's what I wanted to say. So, if we're given a vector v in big V, so we're given one of these, there's a unique way of expressing it as a linear combination of the betas that are in my basis B. That's thanks to this theorem. Okay, great. Well, what that's saying then is that if I want to specify V, one way that I could do it if big B is given to me, one way I could do it is to specify which linear combination of the elements of big B gives rise to small v. And how can I specify a linear combination of these elements? Well, I could specify it by telling you the coefficients of these elements. And notice how the ordering comes into play here, the ordering on the basis. If I just give you a list of numbers, okay, and that list of numbers is inherently an ordered data structure, then you can associate to each element of that ordered list, the associated basis vector, right? Because the basis is also ordered in the same way, same length, etc., right? So I just have to give you n numbers. Those are the coefficients of the linear combination that you would build from these betas to construct V. And that is what we call the representation, is an organized sort of list. We orient that list as a column of numbers, and we think of it as being an element of Rn. Okay, so definition. Okay, we call it the representation of V with respect to the basis B denoted rep sub B of V, okay, is equal to a1, a2, all the way down to a sub n, where v is equal to a1 times beta 1 plus a2 times beta 2, all the way up to an times beta n. And again, the thing that needs to be emphasized is that because the betas form a basis, because of that, these a's are unique. There's only one choice of the a's which gives rise to this v. Okay. Okay. So what I want to do and this was stuff that we talked about last time, and I realized we're 15 minutes in. That's okay. um, it's important to say the words that I said at least once. What we want to do now is maybe let's work with an example of us figuring the representation for some vector space. So here's an example. Let's think about, how about p sub 3? So recall this is the space of, I'll say vector space of polynomials of degree less than or equal to 3. Okay, so what's the dimension of this vector space? Well, to answer that, you would need to know a basis for this vector space, which is, we talked about a basis, which was 1x x squared x cubed. Did I say that right? 1x x squared x cubed. Yeah, 4-dimensional vector space is what this is. Okay. And so we can take, just as a first pass, our basis b to be equal to, 1x, and maybe I'll call it b1, just because I want to develop some other bases in just a moment. X squared and x cubed. So those are my 4 basis elements. There's my p3. And I'm going to take an arbitrary polynomial. I'll just pick one. I'll take 3 plus x minus 2x squared plus x cubed. I wish I didn't make it so complicated, but it's too late. Okay, whatever. So there's an element of p3. Can we all agree? That's a polynomial of degree 3. And I guess I wrote it in the other order. I usually, like in most classes, you write your polynomials in descending order, I guess, but I did it this way. Why? I don't know. I guess I was anticipating this basis coming into play. So what is the and let's give this thing a name. Let's call this vector here v. Okay, I'm thinking of it as this v right here that we're going to be representing with respect to this basis. So then we can write down the representation with respect to b1 of v. And this is easy because we ask ourselves, what linear combination of the b1 of the elements of b1 give rise to this polynomial? And the answer is, well, we take 3 times the first, 1 times the second, -2 times the third, and 1 times the fourth. So we get the representation 3, 1, -2, 1. Okay. I guess I should say this is a basis, right? That's obvious, but I just want to state that out loud. Okay, great. Now, we could change the basis in a number of different ways, and that's going to have an effect, of course, on the representation of v with respect to that basis. So, for example, if I was to define b2, maybe I'll do that down here, b2, by reordering maybe these entries. Like let's say that I made b2 be the order, the basis x squared x cubed 1x. Okay. Then what would the representation of the same vector v, same one, but now with respect to this new basis b sub 2. So what would rep sub b sub 2 of v be? Go ahead. Oh yeah. So remember how I said you should actively consume? Here's what I would like you to do. Pause the video, write down what you think this is. We'll unpause and then get to it. Okay. And you could, so hopefully you see the way that the ordering of the basis matters here, because what we need to do is make sure the first entry of our four tall column vector, we need to make sure that the first entry corresponds, the first entry is the coefficient of the first basis vector in B2 in the linear combination of V. Yeah. And so that's going to be -2. Hopefully you understand what's just happened. Then we use x cubed. We see how many x cubes we need. We need one of them. We see how many ones we need. We need one. We need 3 of them. My bad. I almost said we needed 1. And then we see how many x's we need. We need 1. Hopefully that's clear. Okay, so that's a calculation unto itself. Let's say that we were to change B1 in the following way. Let's say we were to make B3 be 1 4x x squared and then -x cubed. And I guess I'm not proving to you the fact that this is a basis. I don't think it's hard to see that it's a basis, but you should convince yourself of that if you're not convinced. It is a basis. What is the representation of V? Same V with respect to this new basis. So pause the video and figure this one out now. Okay. So if I look at how much of 1 do I want to use, well, I see that because I have that constant term of 3 there, I guess I want 3 of this 1 here. So that's going to be my first entry, 3. What about my second entry? So the basis vector is 4x. How much of 4x is going to get used here in V? Actually, maybe it would be worthwhile for me to actually sort of write this out. So we know that we want to express this V as a linear combination of these vectors. So we can make that sort of apparent to ourselves in the following way. Here's the calculation I'll do. We have 3 plus x minus 2x squared plus x cubed. Can't I write 3 as 3 times 1? I'll just do that kind of thing. And the reason why I write that, which is normally a really dumb thing to write, is because 1 is the first basis vector of B3. So I'm using 3 of that one. How much of x am I going to use? Well, I want to write some number times the second basis vector, 4x. But I know that because there's only 1x here, I'm going to put 1/4 here. Right? 1/4 times 4x is x. For the third term, I'm going to look here. How many x squareds am I going to use? Well, that's not that hard to figure out. That's going to be -2 times... Oh, I wish I didn't do that. Oh, well. I put it in parentheses. Okay, tell you what. What I could do is use a different color. So maybe I'll color the basis elements black. There's 1. There's 4x. So -2 times x squared, and I'll write that in black. And then finally we have x cubed, which is 1 times x cubed, right? Oh, I'm sorry. Oh, we want to write -x cubed, right? So we should write plus -1 times -x cubed. Same logic, right? Now, the virtue of all of this is that it clarifies what the coefficients are that we're using in constructing V. This was our V. In constructing V as a linear combination of elements of B3. Right? Here are the coefficients. And so I can just copy those now. So 3, 1/4, -2, and -1. Okay, great. Now, of course, these are relatively simple modifications on a relatively simple basis. You see what I'm saying? Like, this basis was super easy. We were just able to read off the coefficients of the literal polynomial that we saw in front of our face. Things got a little bit more hairy when we introduced these kinds of complications, but it wasn't hard in principle. But you could imagine there being much more complicated bases floating around. So let's move to a different piece of paper. I'll copy what we had here. Sorry, move some stuff. My desk is a mess. So example continued. That's continued. Yeah, so we had a vector v in P3, which was 3 plus x minus 2x squared plus x cubed. Let's pick a more complicated basis, okay? And see how we might go about figuring out what the representation of this v is with respect to that basis. So let's pick a basis. We'll call it B4. I don't know. There's lots of choices. Maybe one thing that, you know what? I'm just going to make something up. And I guess I'll hope to God that it's a basis. 2 plus x cubed, negative x plus x squared, 1 plus x, and maybe, oh, I should do a 3-term polynomial, huh? How about x plus x squared plus x cubed? I don't know what I've done here. I don't understand what I've done here. But okay. I just hope that this is a basis. It would be very unlucky if it wasn't a basis, but less unlucky when you want to make all of your numbers nice. So you don't want any coefficients which are not 0, 1, 2, or they're negatives. Then you really do run the risk of accidentally writing down a collection of 4 polynomials, which might be, like, for example, a linearly dependent set, right? Or maybe it doesn't span. I think this does span, but I'm concerned about some kind of non-trivial linear relationship happening there, and thus everything blowing up in my face, in which case I would stop this recording, delete this file, you'll never see this, and then I'll try again with a second go around. But let's be confident, okay? I think this is a basis. I don't know for sure. How would we determine, okay, how to express this v as a linear combination of these vectors here? Well, let me show you the sort of how it breaks down, because it basically turns into a linear system. All right, so here's the idea. Can I give these names? I'm going to write these beta 1, beta 2, beta 3, beta 4. What we want to know is what are the a's in a linear combination? What are the coefficients of a linear combination of these betas which give rise to v? So we essentially want to solve v is equal to a1 beta 1 plus a2 beta 2 plus a3 beta 3 plus a4 beta 4, right? We want to figure out the a's which make this happen. Well, we know what v is. It is 3 plus x minus 2x squared plus x cubed. Oh my god, I'm really going to do this, am I? Okay. And then, oh my god, I'm really going to do this? Okay, I'm going to do it once in my life, and then I'm never going to do it again. So I really, really hope this is a basis. This is exciting. So we're going to take a1 times b1. That's going to be a1 times 2 plus x cubed. I'm just literally copying what beta 1 is, plus a2 times negative x plus x squared, plus a3 times 1 plus x, and finally a4 times x plus x squared plus x cubed. Okay? Now what? Now I'm going to collect up I'm going to basically distribute all of the a's over these polynomials and collect up all the like terms like we did maybe in 8th grade, right? And if I do that, what we get is, I'm just you're sophisticated enough that we don't have to do this with too much gory detail. So I have two A1s, and I'm looking at constant terms, and then I have negative A2 x's. No, there's no constant term. I'm sorry, no constant term in this term. Great. How about here? We have an A3 as our constant term, and here we have no constant term there. So that's my constant term of my polynomial. Next, I'm going to look at things with degree 1 terms. So that's negative A2, negative A2, and then here we have plus A3, and then here we have plus A4 times x, right? Then I look at x squared terms. So that's going to be A2 plus A4, wait, one sec, times x squared, and then let me just finish this computation. I need to look at x cubed terms. So I have A1 times x cubed here, and then A4 times x cubed. So that gives us this equation. X cubed, my bad. Okay, wait, I have to pause my recording. Sure. Okay, sorry, brief interruption. Okay, so here is us collecting all the like terms, distributing all that, getting this. Now we compare coefficients. Okay, so what we know is that the only way that two polynomials can be equal to one another is if their coefficients are all equal to one another. By the way, that's a little bit of a linear algebra statement in and of itself. You might think about why. But yeah, what we can do now is say, okay, 3 is equal to 2a1 plus a3. Maybe I'm going to write it in a slightly different order. So we can deduce from this that 2a1 plus, and I'm going to write it in a, well, that's fine, a3 is equal to 3. Compare coefficients for the x terms. We get negative a1, no, a negative a2. I'm really liable to mess this up. A4 is equal to 1. Okay. Then looking here, we get a2 plus a4 is equal to negative 2. And finally, a1 plus a4 is equal to 1. Okay. Now, can we agree that this we can express using an augmented matrix, right? Where we're going to have 4 columns corresponding to the 4 A's, the A1, A2, A3, A4, and then one more augmented column corresponding to this. Because this is, after all, a linear system in 4 variables. The 4 variables being the A's. Okay, and we want to figure out what are the values of A which make this happen. So we get something like 2, 0, 1, 0, 3. That's the first row corresponding to this first equation. I'm going to have 4 rows total. 0, negative 1, 1, 1, 1. Then 0, 1, 0, 1, negative 2. And then finally 1, 0, 0, 1, 1. So there is my augmented matrix. Okay. Now, of course, what one could do, okay, is row reduce this. But of course, that's a lot of work. And I already did too much work for this particular example. Hopefully it's instructive because this was pain. What I'm going to do instead of actually solving this, I think, is put it into NumPy. I'm going to solve this inside of NumPy, and we're just going to see what happens, okay? I have my NumPy window set up here. No, that's not it. Here. Yeah, I have Jupyter Notebook open. So let's create a new notebook here. And let's just do this from scratch, shall we? Okay. So first move is to import NumPy. And as usual, we do this. Now I'm going to I'm going to break this up a little bit. I'll break this up into the matrix A, which is just the, so just real quick going back, I'm going to make, I'm going to make this part here, of course, be that matrix A that we have been working with. And then, of course, this is my B. And what I'm looking to do is solve the equation AX equal to B, right? AX equal to B. That's what I'm looking to solve. That solving that is solving this linear system, because the X's will tell me the values of A1, A2, A3, and A4 in sort of a 4x1 column, right? Tell me those values of A's, which give rise to this B, which solve this linear system is what I should be saying. Okay, so let's go back to Jupyter. We're on Jupyter now. Okay, and so yeah, let me enter. Where's my Jupyter? Let's enter some of this information in. So A is going to be a 4x4 MP array. And here we go. 2, 0, 1. No, it doesn't like 2, 0, 1, 0. First row. Second row is 0, negative 1, 1, 1. Third row is 0, 1, 1, 0, 1. And last row is 1, 0, 0, 1. Close. And that should be our A. Let me just make sure that A is happy. 2, 0, 1. Yeah, yep. That looks okay. That looks okay. Okay. Now I'm going to define B. B is going to be an np.array. And it's a column vector. Okay. So one trick that you can do is enter it as a row vector, which sort of cuts down on the number of brackets that you'd have to do, like this, and then end your thing with a dot transpose like this. And I think this works. Let me just make sure. What does B look like? There we go. That's a column vector, right? Nice. And then we can use the following command to solve this linear system. So I'm going to call X the solution when I solve this system. So I'm entering the matrix A and I'm putting in the vector B here, and we want to solve this system. So if I do that, oh, I should print out what it is. Oh, there it is. There are the coefficients. Oh my goodness, thank you. There are the coefficients of the linear combination, which give rise to this thing here. So let's take this. I'm going to write this information on my paper here. I'm going to write it out. So A1 is equal to 1.5. A2 is equal to negative 1.5. A3 is equal to 0. And A4 is equal to negative 0.5. Okay. So thank you, NumPy, for your service. I don't need you anymore. So let's go back to here. Oh, you couldn't see that because there you go. Now you can see the result of that computation. Okay, great. Let's go back to here. And I wrote all that information down here, okay? Same numbers. So what are we saying? Because remember what we wanted. We wanted the representation of V with respect to B4. Yeah? And now that we have the coefficients of the linear combination, remember, what are these? These are the coefficients of the betas that constitute V. And so now we can write this down. Rep sub B4 of V is equal to the column vector 1.5, negative 1.5, 0, and negative 0.5. Okay. Hopefully that makes sense. Gosh, I really hope that's right. I feel unsure for some reason, but I'm not sure why. That's probably just, I don't want to think about it anymore. Okay, great. So wonderful. Yes, that's how we did that. All right. And it turns out that all of these computations like this sort of have this flavor. Okay. Um, and so what I want you to try to do, well, maybe not. Maybe we'll do this together. But let's just take a quick break. What I want you to do is think about and review this computation. Make sure you understood what happened. Maybe rewind the video and just replay it for yourself. But the sort of feeling I want you to feel is that there was this move where we went from expressing the vector as a linear combination of the basis vectors. We sort of massaged things out, and what we ended up with was a linear system. Yeah, a linear system that we could then solve using a tool like NumPy, or which we could have done by hand if we were a little bit less lazy and willing to endure the tedium by doing Gauss-Jordan reduction or row reduction and all of those kinds of things, right? We could have done it that way. But what that netted us was this expression here. All right. Now, there's so many words that I want to be able to say, talk about things like linear transformations and things like that. But I think we'll set those discussions aside for a little bit later. Let me encourage you to maybe just take a little breather. Let's take a 2 or 3, 4, 5-minute break. Pause the video. Go about your business. Let's come back and then we'll talk again. Okay, I'm gonna sip my coffee that my wife just brought me very lovingly. Okay, see you in 5 minutes. Okay, back to it. Let's go back here. How do I want to frame this discussion? Okay, so here's what I want to say. It's not a coincidence, of course, and you can probably feel this in your bones. It's not a coincidence that when we took this vector v from the 4-dimensional vector space p sub 3, that we ended up getting a 4 tall column vector. Because we understand 4 tall column vectors are elements of a certain other vector space, not P3, a certain other vector space called R4. And R4 we know is also 4-dimensional. So there's this sort of matching of dimensions, and maybe it's not so surprising that we can take this element of a 4-dimensional vector space P3 and represent it using an element of a different 4-dimensional vector space, namely R4. I want to sort of interrogate that a little bit, maybe more abstractly than we've been doing, just so we get some sort of general facts under our belt. So we can view this rep sub b thing, we can view that as a function. So we can view rep sub b as a function from V, the vector space V. So now I'm sort of going back to the framework that we started with before we were doing examples. So remember the framework. The framework that we started with is that V is an arbitrary vector space, finite dimensional vector space, and B is a basis for that vector space. And we can view rep sub B as a function from V to Rn. Now, the mathematical way that we could write this, because we like having notation in mathematics, is to write something like the following. We have a function rep sub b. It eats elements of v and spits out elements of Rn. So it eats elements v here and spits out their representations they're the n-tall column vectors consisting of the coefficients that are needed in assembling that vector v as a linear combination of the elements of the basis b. So we have a function. Why is it a function? Because every vector v is uniquely expressible as a linear combination. That's the theorem. The theorem that we proved last time and that I cited here. Vector v, if uniquely expressed as a linear combination of elements in B. So this theorem guarantees that this is in fact a function. Cool. Now, again, I want to sort of say words about this function because this function is not just, it's not, it has a lot of structure, this function. It has structure which is very respectful of the structures that we know V and Rn to have. Now, V is an abstract vector space. I'm not specifying it. I'm not making it concrete. It is any vector space, okay? Finite dimensional vector space here. N, of course, maybe I should say, where N is the dimension of V. I probably should have said that out loud. Yeah, where N is the dimension of V. And so, because V is a vector space, we are sort of, if we want to sort of understand this function better, here's my thinking, we should make sure that we understand what we know about V in the abstract. For like, that is to say, if all we know is that V is a vector space of dimension n, what do we really know? Well, we know it's got a basis B. That's sort of supplied to us, right? We also know that V has a notion of addition, vector addition, and of scalar multiplication. Those come out of course, the definition of V as a vector space. So if we want this, if we want to promote this function from being a mere function to being something a little bit more special, we might ask, how does this function sort of interplay with the addition and scalar multiplication conditions, or gadgets rather, operations that we have on our vector space V? That's sort of one way in which you might think about why we are going to assert the next theorem. This is going to be a two-parter. First part, rep sub B. If we take two vectors in big V, like V1 and V2, and we add them together and then ask about the representation of the sum, guess what? That's the sum of the representations. And the way that math nerds would talk about this is to say that rep sub B respects addition. Because there's a notion of addition on V by virtue of it being a vector space, and there's a notion of addition on Rn, also by virtue of it being a vector space, where you just add the entries together, right? Rn is the set of all n-tall column vectors. You just add the entries, okay, entry by entry. And so this addition, look at where my pen is pointing. No, not yet. Right there. Yes. That addition is happening in V. Yeah? Because that's the sum of two vectors in V. But this addition right there, that's not happening in V. That's happening in this other vector space, Rn. Okay? But the assertion of this theorem is that rep sub B again respects that addition in exactly this sense, that when you take the sum in V, rep sub B translates that sum into the sum of a more familiar space. Let's say that's not really relevant, but of this other vector space Rn. Okay. Second point, and this has to do with scalar multiplication. If we take rep sub b of a constant c times v, then this is equal to c times rep sub b of v, where c is an element of the real numbers, so it's a scalar. So this is the statement that rep sub b respects scalar multiplication. This scalar multiplication right here is happening in V. That's granted to us by the definition of vector space. This scalar multiplication is happening in Rn, where you multiply every entry of the vector by the column vector by the same constant c. Okay, so I want to prove at least the first bit of this. It's not hard. At least I hope it's not hard. We'll see. And then I'll leave the second one as an exercise for the viewer. Okay, let's proof of one. All right, so let's say all right. What should I do? Okay, I guess I should do the following. Suppose yeah, I guess I should do the following. So suppose rep sub b of v1 is equal to let's call these a's, so a1 through an, and rep sub b of v2 is equal to let's just use b1 through bn. Okay, so these are the representations of v1 and v2 individually. Well, then of course what that's communicating back in the universe of V, in this universe, is how to construct V1 and V2 as linear combination of elements of B. Then, and maybe I should just establish this notation somewhere, maybe up here, B is the basis beta 1 through beta, oh, this is going to be really interesting, beta n. Are you excited? Because the betas are going to mix with the lowercase b's. I'm very excited. So then this implies, these two statements here imply that V1, for example, is equal to, A1 beta 1, all the way up to AN beta n, and that V2 is equal to B1 beta 1 plus Bn beta n. Okay. Great. It's not so bad. Then, what's a V1 plus V2? Well, this is easy. We just add these two things together. So I could literally just write A1 beta 1 plus plus AN beta n. And we add to this all this mess. Bn beta n. Okay. But we can collect like terms, right? Because these two terms are like terms, okay? And by rules of, all I'm using here are rules of vector space operations, right? We know that one of the rules is that scalar addition, is that scalar multiplication distributes over scalar addition. So I could combine these two terms, for example, into A1 plus B1 beta 1. Do you believe that? Yeah, because one of the axioms, I know there's 10 of them, and you have to be insane or you have to have mental issues to have all of those memorized. But one of them that I've memorized is that if you take is that when you have the sum of two scalars, okay, sum of two scalars, and you scale a vector by the sum of two scalars, that can break up into that you can distribute the beta 1 over that sum. Okay. And then we have an plus bn similarly here. Okay? Well, but that points to exactly what then rep sub b of v1 plus v2 is. This is equal to a1 plus b1. That's the coefficient of the beta 1. Dot, 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 all the way up to an plus bn, the coefficient of beta n. But back in the Rn universe, this can be easily expressed as the sum of these two vectors, these two n tall column vectors, right? Like, duh, this is how you add these things together, right? That first one there, that's precisely rep sub b of v1. You see where my other hand is pointing right there? Look. And then that's precisely rep sub b of v2. So I did it. This is equal to that. And that's the end of proof. I'll leave 2 as an exercise, okay? But the real point that I want you to feel, the feeling that I want you to feel, is that, okay, V is a vector space. What's a vector space? It's a collection of vectors together with addition and scalar multiplication. Those are the two operations which are central to defining V. And it's important that we, because we like being abstract, remember my analogy about climbing the mountain of abstraction, we want to have theorems, we want to have results, we want to understand vector spaces sort of as a whole. We want to take a sort of global view. What kinds of statements can we make about vector spaces where all we know about those vector spaces are the fact that it has vector addition and scalar multiplication? We want general facts about that. Now, what we've just established here is that we can define a function as soon as we define a basis. We can define a function from the vector space to a very well understood vector space Rn, which, by the way, has all sorts of like emotional baggage associated with it, okay? Because we've been learning about and getting to know Rn for like our entire lives, it feels like, okay? We have a lot of feelings that we feel toward Rn, okay? Whereas I hope V should feel much more alien and strange and austere, and without all of the florid connotations that might come about when you're thinking about something like Rn. Like when you think about R3, you might be thinking like all of these other things, like, oh my God, there's a cross product, and oh my God, I can define parameterized curves and helices and all that kind of stuff. But no, we're not talking about all of that when we talk about this vector space big V. But there's a way of representing big V, okay, as an Rn. So that if we want to, we can kind of bring all of those emotions that we feel about, I'm not sure why I'm saying it like this, all of these decorations that we feel about Rn, we can bring them back to V via this map, rep sub b. We're going to make all of that more precise later when we talk about how rep sub b is in fact what we call a linear transformation. It being a linear transformation is the fact that it respects vector addition and scalar multiplication. All of the structure, in other words, on V is accounted for by rep sub b. Maybe that's a great way of saying it. I like that way of saying it. All of the structure on V that we're allowed to talk about, which are the vector addition and vector scalar multiplication. That's accounted for by rep sub b because of this theorem. It's very powerful, right? Because as soon as you give v and a b, you can sort of think about things in terms of Rn. That in some sense, v is Rn, okay? V and Rn are the same as soon as you specify a basis, b. Okay, great. Now I would like to suggest a problem for you to do. And what I would like for you to do with this problem is probably use something like NumPy to do this problem. And I want you to think through it. I'm going to give you the first bits of it, maybe, because it's a little bit hard to think about, maybe. And that's the following. And part of the reason why it's hard to think about is because of what I was saying before. It's because we bring a lot of emotional baggage when we think about something like Rn. We bring a lot of that kind of stuff. We sort of attach it to Rn. But what I want us to do is think for a moment about what would happen if our abstract vector space here, V, was Rn. So, and we give a funky basis maybe on it. So I essentially want to repeat the exercise, the kind of exercise we just did, where we were representing a particular polynomial with respect to a particular goofy basis. The goofy basis there was B4, remember? B sub 4, not the word before. B4. Here's B4. And we represented this vector V using this thing here. So I'm going to end the lecture here with just this exercise. So, exercise. To make sure that you understand what's going on here. And what I want you to do with this exercise is give me the answer via email. Just send me an email with the answer to this exercise. And it's going to be due by the end of next week. And the answer is very simple. Here it is. So consider V equal to R4 now. Okay, so V, what's playing the role up here of V is now R4. R4 is a four-dimensional space. So if I give you a basis, if I give you a basis of R4, then that defines a map of R4 to Rn, where n is the dimension of R4. The dimension of R4 is 4. So that's a map from R4 to R4. So let's specify a basis. And it's not going to be the nice basis. I'm going to make it up. Let B be the basis. So now what do I have to specify? I have to specify for you an ordered set of 4 vectors in R4. And here's what it's going to be. 2, 0, negative 1, 1. 1, 2, 0, 1. 1, 0, 1. Oh my God. 1, I'm really nervous. And then how about 0, 0, 2, 1. Oh my goodness. I'm so nervous. But what I'm going to do as soon as I turn this video, because I just made those numbers up, and once again I'm in this awkward situation where there's okay. Here's a theorem. If you mash these vectors together, if you take 4 vectors in R4, or n vectors in Rn, and you mash them into a matrix where those vectors are columns, remember how we talked about the density of non-singular matrices among the set of all matrices? That if you randomly choose a matrix with probability 1, it will be a non-singular matrix? Well, it turns out, and I don't want to talk about this right now. We'll talk about this later. It turns out that the columns of a non-singular matrix form a basis for Rn. Okay? So if I've chosen 4 randomly chosen vectors in R4, it seems like with high probability that should be with probability 1 that should be a basis. But the thing is, like, I wanted to be nice and make sure that the numbers that I used were reasonable numbers, like not 5 and 7 or pi or square root of 7. But numbers like 1 0 -1 2 0, you see the numbers I've chosen here. But this makes me nervous because this is not really randomly chosen any longer. Although I just sort of vomited out these numbers, sort of quote unquote at random, you know what I mean? They are plucked from that limited set of numbers because I wanted to be nice, okay? So now the probability that this is a basis has gone down drastically, okay? And it could be interesting to figure out what that is exactly. I'm not really interested in doing that right now, but I'm hoping that this is a basis, because if it isn't a basis, then this exercise is completely screwed. So like I said, as soon as this video is over, so maybe I should edit this whole part out of me being a little bit unconfident. I mean, it's not about confidence or unconfidence. It's about whether or not when I rolled the dice, did it come up, snake eyes or not. When I rolled the dice on these numbers, did it come up as a basis or not? Or not a basis or a basis. I'm really hoping it's a basis. Okay, so suppose B is this. I want you to find rep sub B of a vector in R4, a vector here. So what vector? We'll make that be 4, 6, -2, 1. Uh-oh. Yeah, sure. I don't know what I did. Does this make sense to you? Now, how should you do this? You should use NumPy. Okay? You might consider following the steps that we did here, but for the polynomials, very similar. You should be able to concoct a linear combo of those which give rise to this vector, okay, which is equal to this vector. So in an email by October, because I'm going to be gone next week, I want this by October 18 before midnight, before 11:59 p.m. on October 18th. October 18th, I want you to send me a list of 4 numbers. Maybe present your answer as an np.array. Okay, you can just give me np.array and then give me the 4 numbers in with proper syntax and all of that kind of stuff for what this is equal to. This is equal to what? Okay. That's enough for this video. I think we'll have another video. And I am working on putting together a homework for you. That's not quite done yet, but that's coming. Okay. Love you. Bye. And I think another video coming. Okay. Bye. Bye.